Now taking a look at logarithmic equations, there's going to be two forms or two scenarios. One will be where we have an equation where not every term is a logarithm. And if that's the case, we may need to use some properties from before, but we will eventually be able to get the equation into the form of log of something equals a number. We'll get it into this form. And the whole idea with a logarithmic equation when we're solving it, the issue will be that x is trapped inside of the logarithm and no easy way to solve for it. However, when we get to this form, we will be able to take this form and rewrite it in exponential form to this form, using our cycle, b to the c equals m, to rewrite it, and then this will be the part that includes our variable, will be outside of anything, any logarithm, and we will then be able to solve for x. So let's see how this works. Well, then we'll talk about this last step as well. So we have log base 4 of x plus 3 equals 2. X is trapped in a logarithm, so we already have the form, log equals a number. So I will use my cycle and have 4 to the second equals x plus 3. Now, from there, we have 4 to the second is 16, and it doesn't get much easier than that to subtract 3 and get that x would equal 13. Now, that is the potential solution, the proposed solution. But we do want to recall, logarithms have a domain issue or domain restriction. The thing you take the logarithm of must be positive. Think back to the graph or just our general rules for logarithms. The domain of a logarithm is everything positive, everything above 0. So this number you get, we do need to, if you want to call it check, essentially, or I'm going to say check the domain is really what you're doing. You're taking this number 13 and making sure that what you plug back into, so x plus 3, just the argument of the logarithm, well, that would be 13 plus 3, which is 16. We just need to make sure it's going to be positive. As long as it's positive, we're good to go. And so 13 would be our solution. That's all you have to do for the checking of the domain. You don't actually check the equation itself. You just check that the final argument of your logarithm is a positive value. All right? Let's take a look at the next one. So 3 ln of 2x equals 12. So before we can convert into exponential form, we do need to get rid of this 3. Now, one easy way to get rid of this 3 is actually to not use the power rule, but instead realize this is just multiplication, so you can just divide it on both sides and have ln of 2x, and in this case it even divided nicely, just down to a 4. So don't necessarily make it harder than it needs to be by making a power rule out of this when you can actually just divide it out immediately. But this ln, let's remind you, is a log base e. So we're looking at log base e of 2x equals 4. If that helps you write it that way to see the cycle, this is e to the 4th equals 2x. And then just dividing both sides by 2 is all it will take to solve for x. Now, e to the 4th over 2, right? That value, we do want to officially check the domain, which will be plugging it into just this 2x. That's all we're checking. So 2x, so 2 times this whole thing, e to the 4th over 2. Well, those are going to cancel and leave us just e to the 4th. And real quickly, just to verify, even though hopefully it's pretty obvious, e to the 4th is approximately 54 point something, 0.6. Definitely positive, right? That's all we need. This is going to work. So we'll have the x, actually, don't write x. We'll have the e to the 4th over 2 is a solution. And again, that's what we call exact. Or we could plug into our calculator e to the 4th divided by 2, and we could get an approximate of 27.299 for approximation. Now, taking a look at this next one, you'll notice we have more than one logarithm, but we do have a term that is not a logarithm, and that's the key to this approach. As long as there's a term that doesn't involve log, then we will use this approach. However, before getting to the approach, the very first step said we need that form, one logarithm equal to a number. So we want to remember our property of combining logarithms here, right? Writing them as a single term. These are both log base 2 combined through addition. So our logarithm property said we can combine them into the multiplication of those insides, of those arguments. Right? That was the log of m plus log of n is log of m times n on the inside. And that's the property we're going to need to do. And also I'll do a little simplifying here. To get to that form, now it is still the case that our x is trapped inside the logarithm, but now we can use our cycle. Now we have log base b of something equals something. Use the cycle. 2 cubed equals x squared minus 7x. So 8 equals x squared minus 7x. Now notice this equation is not going to be a linear equation, right? We've got x squared. So instead, there's no way to just isolate or solve for x. So instead we will move our terms to one side, set equal to 0, and always at first hope it factors, which this one does. So to solve this equation, that factors into two binomials. Numbers that multiply to -8 but add to -7 are -8 and +1. And so we get our two solutions, setting each of those equal to 0 of +8 and -1. Now, all this work, do not forget, anytime you're solving a logarithmic equation, and notice we never had to do this with exponential equations earlier in the section, but when you're solving logarithmic equations, you do have to check the domain. So, checking 8 in each of these individual logarithms from the beginning, right? There's two different logarithms. Well, x being 8, that's positive. And x minus 7 would be 8 minus 7, which would be 1. And that's positive. So, checking x equals 8, good and good, right? Again, taking this 8 value we got and making sure that it didn't cause a problem in either of those logarithms. All right? So that was checking x equals 8. Now let's check x equals, oops, it's supposed to be a -1. Well, the very first logarithm was log of x, and if I look at x and I plug in a -1, that is less than 0, right? That's no good. We cannot let our value from our solution be plugged into the original equation and have an issue with the domain, or we're not allowed to do that. Turns out it doesn't work here either, but it doesn't matter. As soon as one logarithm would have a domain issue by plugging it in, that doesn't work. We're not going to keep that, meaning -1 is not a valid solution, okay? Meaning 8 is our only solution to this problem. We can actually get multiple solutions that aren't all actual final answers. Again, they're what we call proposed solutions. And we have to check the domain of every single logarithm to decide if they actually are valid.